Well, good afternoon, ladies and gentlemen. Thank you for being here today. I would like to give you an overview of the capabilities and performance of high reliability solder masks for e-mobility applications as well as for lighting applications. A very short introduction to Peters, who we are, what we are doing. Next year we are going to celebrate our 50th anniversary. We're a company focused entirely on coating innovations for the electronics. So we basically have two fields. One field we're working on, it's approximately half of our business, is related to the manufacturing of printed circuit boards. Peelable solder mask was an invention of Peters. Heatsink paste screen printable are another invention. Various solder masks, carbon conductive inks, and the field of assembly, where we protect assembled printed circuit boards from, say, humidity influences. When we're looking into solder masks in general, there is one thing they have in common quite clearly, and that is the basic formulation. So typically we distinguish between the resin component, the A component, and the hardener component. And the most important ingredients in this case are the binders, which determine the overall performance of a coating, the dielectric properties, the resistance properties, the fillers, which are functional fillers, like talcum for example, which improve adhesion of the material, the wetting of the board, and then of course dyes, pigmentations to give it a color, certain additives to promote, say, flow, as well as solvents to adjust a certain viscosity. Now if we look at the hardener component, there are basically three ingredients in general. So that's the photoinitiators, which enable the photoreaction, the photopolymerization, to create the structures on the board. We have again the solvents to adjust the viscosity to make sure the material can be used in, say, curtain coating, screen printing, or spraying, for example. And the hardener component, which leads to a cross-linking with the binders and gives the final properties of the product, whether it's resistant in finishes, for example. So basically this is very common to all of these coatings, no matter which brand you are using. To give you an idea, a solder mask can consist of up to 20 to 25 different ingredients. So it's a quite complicated system. I was talking about the application modes. What is very important to keep in mind is that depending on which region of the world you're looking at, there are preferences, very clear preferences in the mode of application. In Europe, still the curtain coating process is predominant. Also a lot of air-assisted spraying, vertical double-sided screen printing, as well as conventional screen printing. Whereas in Asia, by far, it is screen printing, horizontal screen printing, and spraying or electrostatic spraying. And keeping this in mind, these differences in application leads to different formulations. So not necessarily all coatings can be used everywhere. If we're looking at high performance solder masks these days, it is very important to consider that when we're talking about high temperature resistance, for example, it's not only the solder mask itself which needs to be able to offer a certain result in terms of resistance, but we also need to consider the base material used as well as the pre-treatment, very, very important, prior to coating. So in other words, when you're using a low TG material, low CTE as well, you're never going to be able, no matter what coating you're using, to stand up, say, to a temperature resistance of up to 175 degrees Celsius. Impossible. So you need to make sure, first of all, that you have the right base material as a basis to work with that. Now, very important is also the pre-treatment of the substrate you're going to coat, especially the copper which is going to be coated. And this is an example of 2000 hours temperature storage at 120 at 175 degrees Celsius. And as you can see here, when we compare pumice brushing, a brushing process, and a chemical pre-cleaning mode using the IN ISO 2409 specification, crosshatch, to determine elasticity and adhesion, you see enormous differences. So forget about brushing or pumice brushing, it won't be of any help. Adhesion is not good. So we are in regions where more than 65% of the coating have lost their adhesion. Now it's totally different using certain chemical pre-treatments where we can actively influence the performance of the solder mask. So here, even after 2000 hours, we have a cross-cut value of 0, which means 0% loss of adhesion. That's what we want to see here. Talking about today's systems then, high performance, high reliability systems, these two additions are important. We're talking about high temperature resistant products with a temperature class 7 according to Bosch, 150 degrees Celsius, and we can go up to TC9, which equals 175 degrees Celsius. That is not only temperature storage, long time, but this also relates to temperature cycling. So we have customers 1000 cycles, 2000 cycles, even 3000 cycles from -40 to 175 degrees Celsius. So that is pretty impressive. These coatings are basically available for spraying, for curtain coating, as well as for screen printing. Now, the differences between these two products are basically, this range is for conventional contact exposure, which requires exposure energies in the range of, say, 600 millijoules per square centimeters. Now, as you've certainly seen here in this hall, there is a lot of direct imaging, high interest in this technology, and for this application, you of course like to have coatings which have a low level of exposure energy, so that you have a fast process. And here we're talking about exposure energies required in the range of, say, 80 to 100 millijoules per square centimeter. So that is pretty impressive. So again, TC9 with these products is not really difficult to achieve. How come that we were able to develop such systems, fast systems with very tight clearances, with very fine solder dams? We made the decision to invest as a coating manufacturer into DI technology ourselves. So we bought a small direct imaging machine to enable us to really do R&D work with the equipment, which is then also used in the field. So yeah, 100 millijoules, as I said, millijoules per square centimeter in direct imaging. But, and that is important, you can also use this coating for conventional exposure. So you can use both worlds. It doesn't necessarily only have to be direct imaging. What is very important when you look at today's coatings, the environmental view on things. So these coatings are free of Ergacure 907 or problematic photoinitiators, which this is going to come on the list of substances of very high concerns, and I'm pretty sure you don't want to have that in your products. Whether you're a printed circuit board manufacturer or whether you are a assembly house, because during soldering temperatures you can have condensation of these substances into your reflow ovens. So you rather stay away, and you should pay close attention to the photoinitiators used and the labeling of these materials. Yeah? So what are we capable to do in DI technology? We achieve solder dams like 40 microns, without any problem. Clearances in the same range are also possible, yeah, as you can see here. So we're actually far away from the good old days of conventional screen printing. You may remember where we were probably able to achieve like 150 to 200 microns resolution. What our customers have asked us for again and again, and now at the show we're finally able to offer it, is special colors for direct imaging as well. So typically today still the special colors solar masks are still formulated for conventional exposure. And with this range in red, in black and in blue, it is possible to also use these coatings with DI. We're talking here about energy levels of say 100 millijoules for blue and red, and because black obviously absorbs a lot of light, we're talking here round about 150 millijoules. So these are readily available, these materials. If you want to test them, happy to supply a sample. Now, if we're concentrating a little more on the classification of temperature ranges for polymer materials or coatings, we see today a limit for the polymer systems at 180 degrees Celsius. We tested up to 200. Electrical properties were still okay, but the mechanics were not good anymore. So sensitive towards a cross edge, for example. Yeah. But 175 either continues several thousand hours or cycling is no problem at all. This is pretty much of a standard, 150 as well. So any decent solder mask today will be able to perform in that range. But of course you have to think of tomorrow. So if you see at the horizon the need for you and your customers to have a higher temperature resistant material, it's probably a good idea to change to a higher temperature compatible material already today, so that you don't have to do it tomorrow, and the other performance as you used to. So you're adding an extra feature of performance to these materials. What we typically see then, if we're talking about base material and solder mask which are not fitting, it's these corner cracks you don't want to see. So this is what people are looking for. Here are some other examples. So you see these tiny cracks here, or here at the conductor, here one as well. So this is something you definitely do not want to see, and which can be excluded with these systems when testing for thermal shock resistance, for example. Now, one interesting point is, if you do these 1000 cycles, the board goes in like this, it comes out like that. Don't be disappointed. It has no influence on the functionality of the material. It is a certain degradation, but that relates mainly to the color-giving substances. So when we test for like breakdown voltage or so, the results are still very good. Yeah. What some customers do, you may call it cheating, I'm not sure. They use a black material right from the start, not the green. So it's black when you put it into the climate chamber, and when you take it out, it is also black, so there is no color change. Yeah? But most customers we are dealing with, they don't have a problem with a discoloration after several thousand hours of testing, because the functionality is still there. Yeah, what you can also do with most of these materials is via plugging. Yeah? So depending on the printing process carried out in horizontal printing, you are capable of filling the vias with solder mask. You apply a step cure to get rid of the entrapped solvents, and you'll have a bubble-free and crack-free filling or plugging of these vias. And what you see here is after 2000 hours, 170 degrees Celsius. And this is an example of a product which failed and what can go wrong here. Yeah, white solder mask. Besides high reliability materials, white materials are asked for a lot these days. This has to do with the implementation of LEDs and being used in all sorts of fields, also strongly growing in the automotive field. So what we use for measurement here is a certain spectrophotometer, as you can see here. And when we're comparing products and looking what their performance is like, we apply typically up to 3 times a standard IR reflow process to determine what and measure actually what the level of discoloration is. Yeah? So this is the profile with round about, that is critical, round about 2 minutes above 200 degrees Celsius. So the first product I'd like to show you is the R6B here, and the speciality about this material is 100 cycles minus 65 to 125 or 500 cycles of this material without showing any cracks. And this material is largely used in the automotive industry. You're going to see that the level of discoloration is a little bit higher than with certain other products, but it offers the advantage of no cracks at all. And for certain applications, like in the automotive field, that is typically what you want to see. So what about the general properties of these materials? It's comparable to a standard photoimagable solder mask, I would say. What you need to keep in mind though is that these white materials are, from a formulation point of view, a challenge. The reason is that you have a very high level of filling with titanium dioxide to hide the substrate, and that means you add up to 30 or even more % of white pigment. And this totally changes the behavior of the coating, the elasticity for example, compared to green, where usually the level of pigmentation is in the range of, I don't know, 3-4% at most. So you're dealing with another beast here from a formulation standpoint, but still, performance is comparable and actually very good. Now, when considering these coatings, like this R6B for example, we first of all look at the LAD values from the C lab, where there is a color room defined and where I can position any color in this room and define it by coordinates. So we are basically looking for the lightness of the product. Ideal black would be 0, ideal white would be 100. And of course we want to be as close to these 100 as we can. And what we're typically interested in are the delta values, before, after. So in this case, it would be before measurement, and in this case, after 3 times measurements. So you see the delta in lightness is just 0.35. Yeah? What we're most interested in though is the delta B value. The reason for this is that in this color system, so white, black, red, green, and blue, yellow, we are looking at the yellowing of the material. So this is the part we're most interested in. Now, with the naked eye, you're probably capable of seeing a delta of 1. If you're really good at it, you can see it. Most people starting from 2. So this is actually quite good. What is interesting as well, and this has to do with the pigmentation, is the thickness. Obviously, the higher the thickness, the better the coverage of the substrate, and the higher the level of reflectivity will be as well. So you have to keep that in mind. 20 microns can be a little on the low side. 40 is okay. I would say as a standard recommendation for these coatings, you're absolutely fine with a thickness of, say, 35 microns. That definitely helps. Yeah, if we're looking at the photometer data here as well, this is the remission over the wavelength of these materials, and the B in this product name stands for blue. So we add a little blue to this solder mask, which makes it a cold white and more difficult to detect by the eye a certain level of yellowing. If you're going to measure it quite clearly, you're going to notice this, and you're going to see in a little while a other emission curve with a pure white, non-blued coating where this looks fairly different. So the red one is no stress applied, the blue is stress applied in terms of IR. This is for a higher thickness here. So this is actually the material with the highest level of reflectivity. Typically we measure at 460 nanometers, and that is above 90 degrees Celsius. But you see the difference to the product previously shown. It's not capable to go for 500 cycles minus 40 to plus 125. Then you may encounter cracks. Yeah? So again here, the performance of this system is what you expect from a good solder mask. Resistances, pencil hardness, moisture and insulation resistance, it all is according to the IPC specification. Here again, the LAB values, and you see here we're at a very high level, 93, even above that, and the delta B, which is extremely low. So with the naked eye, you wouldn't be able, as I said, threshold like 1, you wouldn't be able to detect that. Yeah, here you see another curve of the remission of this R8 material, and you see this dimple, which was here, is not visible and measurable, which is more important with this product. So again, no stress applied, red, 3 times stress applied, blue. This is with 40 microns, where we are also in this remission curve clearly above 90%. Thank you very much.